So, good afternoon, everyone, and welcome to the Circular Materials Conference Research and Innovation Cauldron. This is a great session, has become something of a tradition at the Circular Materials Conference. It's really an opportunity for us to hear about a range of different research activities and other initiatives that are part of the circular materials drive towards circularity. The way we're going to run this session is that we've got 7 presenters all lined up to give you a very short, high impact presentation about their work. No mean challenge for them because they've been working sometimes for years on in-depth analysis and work, and to try and translate that into simple a communication is a challenge in itself. But after we've heard from all 7, what we're then going to do is invite you to go into a breakout room with the speaker of your choice, so you can learn and interact with them a little bit more. So that is the plan. So right at the start, let me just get my... So our first person in the ConverStation Cauldron is Malvina Roci, who's from KTH, Royal Institute of Technology. Malvina, great to have you with us. Your title is Circular Manufacturing Systems, Concept, Characteristics and Implementation Challenges. Looking forward very much to hearing the work that you're involved with. Over to you.
Thank you for the introduction. It's an honor to be here today. I'll start with sharing my screen. Do you see my screen now? Yes.
Yes, good.
So my name is Malvina, and I'm currently pursuing my doctoral studies at KTH Royal Institute of Technology. And my research topic is circular manufacturing systems. So in this session, I will introduce to you the concept of circular manufacturing systems, their characteristics, and why is that a need for the manufacturing industry to shift to this new paradigm. As we heard several times this morning, is that the linear consumption model of today's economy, which is based on the concepts of take, make, use, and dispose, is a very wasteful system. As you can see in this graph, which is basically showing the flow of material resources in European Union, only a small fraction of the materials is looped back for value recovery. So when we zoom in into the manufacturing industry, we can see that the manufacturing industry is a major consumer of the energy and material resources, and it is also one of the biggest contributor of waste generation. So from this data from Eurostat, also referring to waste generation in the European Union, manufacturing industry is the 3rd biggest contributor of waste generation, coming after construction and mining. So there is a great potential for improvements in this sector. So circular manufacturing systems are systems that are designed intentionally for closing the loop of components and products, preferably in their original form through multiple life cycles. So what we propose is a systemic approach that tries to consider a life cycle approach going from raw material extraction all the way to end of life through the different value recovery strategies. And what I also would like to highlight here is that nowadays there are a lot of attempts to recover the value of products and materials through reuse and refurbishing, remanufacturing, and recycling, but neither the products nor the systems are actually designed for closing the loop. So this is what we call closing the loop by chance based on business opportunity. And what we propose in contrast is closing the loop by design. So you design from the beginning the products to be used for multiple life cycles. We recently published a book chapter in the Handbook of the Circular Economy where we propose a framework for implementing circular systems. And what you can see here is a systemic approach that tries to integrate the aspects of business model, product design, supply chain, and ICT. So there is a need for innovative business models that enable economically viable ways to reuse products and materials. The products need to be designed for closing the loop. So we talk about design for value retention, design for a life cycle extension, and so on. And companies that are moving towards circular systems, they also need to have the right supply chain infrastructure. So they need to have the infrastructure in place to collect the products so then they can do value recovery and redistribute them again in the market. And in all of this, ICT plays a crucial role because in order to keep these all elements of the system under control. What we also did, we tried to look at some relevant industrial practices that have actually implemented circular systems in the manufacturing landscape. And they also employed this systemic approach. I reported here 2 examples, but in the book chapter we have more examples. So we look at Caterpillar, for example. In terms of business model, they implemented a buyback and a reselling model. They have designed the products for multiple life cycles. And in terms of supply chain, they have a Caterpillar distribution network that enables them to take the products back for value recovery and reselling. And also ICT is very important because they employ ICT in order to do predictive maintenance so they can intercept the products before they break. And Xerox is another pioneer in terms of implementing circular systems. And except from take back and reselling, they also implement this paper copy, or which is this result-oriented business models. And when we move towards this more service-based business models, when the company keeps the ownership of the products, the role of ICT becomes even more important because it's very important for the company to trace and track the product throughout their life cycle so they can also offer prompt servicing and repair. And then I would like to quickly introduce to you the methodology that we employ to analyze and characterize circular manufacturing systems. And what we usually do is complex system modeling and simulation. Usually there are 2 types of tools that can be employed, analytical tools and simulation tools. Analytical tools, which is basically equation-based tools, they show limitations when we are dealing with more complex and dynamic systems that have nonlinear behavior, when there is a time and causal dependency in the system, when we are dealing with a large number of parameters, and there is uncertainty in the system. So when we are dealing with this kind of complex and dynamic systems, simulation models are a better answer. And what we propose is using a multi-method simulation strategy because there are 3 major modeling paradigms. They are namely discrete event, agent-based, and system dynamics. As you can see here in the left-hand side, these simulation modeling paradigms serve different abstraction levels. And since circular manufacturing systems are dealing with different elements and there are different stakeholders involved in the system, different levels of abstraction are needed to actually be able to capture the complex and systemic nature of CMS. So to summarize, modeling and simulation can be employed to evaluate the economic, environmental, and technical performance of the system prior to implementation. And what I would like to highlight is that these kind of tools are very important in a context where the implementation of circular system is in its infancy, so there is not so much market available data. So the companies can employ these tools to analyze different scenarios and evaluate their economic and environmental performance in a risk-free environment before finding out the best solution to implement. And typical simulation outcomes in terms of economic, environmental, and technical are reported here. So in terms of economic, one can analyze different cost streams over time and also the environmental impact over time. And when we are talking about multiple life cycle products, what we notice is that reverse logistics, since we have multiple flows of the product over the life cycle, becomes an important factor. So these kind of tools actually allow you to highlight hotspots for improvements. And in terms of technical performance, for example, it would be interesting to see or to evaluate or forecast quality, quantity, and timing of return flows. Because once you know when your product will be back and at which time and in which quantities, then it will be easier to plan the circular business models and implementing them. And to conclude, I would like to introduce one of the European projects that we are working on, which is basically a large-scale demonstrator of circular systems in 2 key areas, which is the white goods and automotive. In the white goods, the company is trying to implement paper wash offerings in 4 European countries, and the automotive sector, the company is Bosch in this case, which is already employing remanufacturing automotive parts, and they are trying to streamline their reverse logistics flow by employing several ICT platforms. And with that, I would like to, thank you for your attention. And I think we can have a closer discussion later on in the breakout session.
Malvina, great presentation and a very important area of work, particularly for business. So many thanks indeed for that, and hope there'll be some take up in the discussion following this. Every business should beat a path to your door following that presentation. So thank you so much for that. Okay, I'm going to leap forward this wonderful potpourri of different programs, and we're going to look at mining wastes next. Huge amount of waste from various mining processes, and does that offer prospects for circularity and for the potential as yet untapped resource? And Marjaana Karhu is Senior Scientist at VTT, the Technical Research Centre of Finland, is with us this afternoon. And I think you're particularly focusing on talc ore mining. It's difficult to think when we have this lovely talc that it comes from a pretty dirty extraction business. But Marjaana, great to have you with us and look forward to hearing your presentation.
Okay, thank you, Peter. I start to sharing my screen. And start the presentation. So good afternoon all, also on my behalf. So my name is Marjaana Karhu and I work as a scientist in the field of industrial circular economy at VTT Technical Research Centre of Finland. And I start with a short introduction of VTT solutions for mineral side stream circular economy solutions, and then go into more detail in that my case study. So at VTT, we are developing solutions firstly for closing the mineral side stream loops. So we will recover the valuable metals as well as finding the way for mineral residue valorization. We also develop solutions for low carbon processing and CO2 capture and binding. And thirdly, we are developing solutions related to data, so solutions for we develop digital tools for circularity and traceability. So we create our excellence in understanding of mineral side stream properties, their processing and their valorization possibilities. And we look into technical viability, but also the economic viability, the regulatory and sustainability boundaries for the utilization. So we have an extensive know-how, the mineral side stream characterization, their process modeling, their processing. We have facilities in lab scale and also in pilot scale. And then we could perform different kind of economic and sustainability assessment also. Then about this case study about the utilization of mineral side stream in high value application. So typically we are looking for high volume solutions for mineral side streams utilization, but in many cases the values are low. So in order to create value in circular economy, we need to put research efforts also to study the possibilities for utilization in high value applications too. So for that case, we have a combination of different solutions for valorization. And this case study that I present today is published in Journal of European Ceramic Society. And it's about feasibility of designed mixture of mineral side streams as raw material feedstock for electric insulation ceramic coatings. And in that study, we have studied two different mineral side stream, and the first one is mining residue, and it's actually the coming from this talc ore mine. And generally, the mining industry residues are the largest industrial waste stream, and globally 20 to 25 gigatons are produced annually. And in Finland, the mining waste compose 75% of all waste that is generated in Finland. And at this moment, some percent of these residues are utilized, but major parts are landfilled, which cause huge environmental and economic disadvantages. The second side stream we utilize in this study is residue resulting from aluminium anodizing process. And the volumes of the side streams generated from that process can be as high as half of the production of the anodized aluminium. And also these side streams are currently mainly disposed in landfill, so no current utilization. So here is now the process for this our case study. So how we develop the value from the side stream. So we start to designing the right mixture of the residues, and we have selected these two side streams, so the magnesite-rich mine tailing and the aluminium anodizing process side stream. And we start the detailed characterization of those side stream, and by making the synthesis design for the chemical compound that we are aiming for this study. And as a next step, we do the synthesis and the processing of these residues in the dry ceramic powder mixture that can be then used as a feedstock for the coating process. And as a third step, we demonstrate the coating process. And in this case, we have utilized a thermal spray coating deposition to produce the ceramic coatings. And as a final step, we characterize the structure, properties, and performance of the produced coatings. And when we then achieved ceramic coatings that show electrical insulation capability at the same level and the considerably lower wear rate when we compare those coatings with the coatings that has been prepared using virgin primary raw materials as powder feedstock materials. So we achieved at the same level and even better properties than with the pure virgin raw materials, utilizing these secondary side stream materials. So to conclude, what are then the benefits for this solution? So we have a huge climate and economic benefits. We can now substitute the virgin raw materials. We could reduce the transportation of raw materials for long distances, and we could also provide longer lifetime of the coated components because we have improved the wear resistance of the materials. And also we can provide secure supply benefit because the materials are now currently used in those ceramic materials are transported from outside EU. So the certain countries dominates currently the virgin raw material markets. So there is a huge supply risk related to those raw materials. So lots of benefits related to this case. But thank you for your attention, and hopefully we can continue discussion in the separate session after this session.
Marjaana, fascinating, really interesting project, not just for what you're developing there, but also as a way of opening eyes and thinking about other possible waste streams from extractive industries and others, and how a discipline of mind can begin to see the possibilities of creative circularity within these areas. So I think this points to a whole raft of different opportunities coming along. But again, if you're interested in that, then join Marjaana in her discussion at the end. So from talc and mining waste, we're going to go to flooring, circular flooring, in fact. And there's an EU-funded project, Circular Flooring, looking at enabling the circular use of plasticized PVC from post-consumer floor coverings, and work being done to develop further recycling processes. Melanie Schulte, Bavarian Research Alliance, is with us this afternoon. Melanie, great to have you with us. And I love this because we're going from all sorts of different materials in a seamless jump. So very interested to hear about the world of floor coverings and circularity. Over to you.
Thank you, Peter. Yeah, it's really amazing to see the various projects and material streams that are targeted. I'm going to share my screen.
It's always the worst moment.
I hope it works. I hope you can see it. So.
You're good?
Good. All right. Thank you very much. So I'm Melanie. I'm not a researcher, in fact. I am more a specialist on EU funding and project communication. So I'm going to present a EU-funded project, which is Circular Flooring, and there we've tried to explain the obstacles and also promoters that we identified in the use of secondary materials, especially in our case, PVC floor coverings. Just very brief, as time is very limited. So we investigate on post-consumer waste flooring, for example, PVC flooring that has been laid in buildings such as hospitals or schools where this is widely used. And the main objective of the project is to establish a holistic recycling cycle for the entire product. So not just the PVC, but also the plasticizers, in fact. And yeah, you will find more information about the project on the website, of course. And we have a very lovely consortium. You might know some of the names there. Very diverse, consisting of industry, NGOs, and research. So yeah, the main objectives is to lessen the pressure on primary materials. So PVC is, well, heavily used in floorings, in window frames, in cables, and flooring itself is more a minor waste stream, but nevertheless, it's also important to find solutions for those waste streams to become a circular economy in Europe. And a major issue is to separate the plasticizers that have been used in flooring 30 years ago when the floorings were produced. As you know, floorings are applied for a couple of years. They have a very long lifetime experience. And the plasticizers used therein are now subject to the REACH regulation, for example. So you're not allowed to use them anymore because they're hazardous to the environment or the consumers, but most of the waste stream is actually landfilled still. So about a third still ends up in landfills, and we try to demonstrate that cycle while, of course, also doing assessments on LCA assessments, social responsibility assessments of the recycled material. So very brief, that's how the project works. So the post-consumer PVC floor coverings are collected, shredded, and we are not dealing with a chemical recycling system. It's a physical solvent-based recycling system. So with that Creasolve a recycling process, the PVC flooring granules are separated or are solved and then separated. So we end up with a PVC and the separated plasticizers that are hydrogenated. And so we have two different material streams. One is the recycled PVC and the second one is the plasticizers. And the idea is to recycle both streams and reunite them in a circular PVC floor covering. So actually having a complete new product out of the old product without really adding much virgin material added or any other materials. And of course, the solvents are hazardous-free substances, needless to say. As we are all experts in circular economy, I guess the benefits for European society are quite obvious. So less pressure on primary resources, a holistic cycle. We have new business opportunities, of course. So we also elaborate on the technologic feasibility, if it's really worth the money to implement such a recycling system on a large scale and have such a recycling for PVC waste. During the project, of course, we face also a couple of obstacles, and that might be eventually the same that you are facing in your project. So in our case, the sufficient material supply for a Kreasolv recycling plant is quite critical. Of course, there is enough material out there. There are floor and PVC floors everywhere. But to date, only 80% of the floorings, post-consumer floorings, would be available because in construction demolition, they get heavily damaged. The buildings, the floors are damaged due to flooding or burnt. So only 80% would in theory be available for collection. And you can imagine the collection rate is relatively low currently. About 10% are actively collected and brought to recycling schemes. One of these is also for example, of AGPR based in Germany. And so the most challenging part here is providing sufficient incentives for the collectors to invest the money and time to collect the PVC floorings and bring it to the recycling plants actually. And with regards to the research, the scientific one that's carried out in the labs, it is a bit of a challenge to obtain virgin-like quality of the secondary recycled materials. So the properties are basically the same, but the color and the structure are slightly different. So we are working on this. And of course, then it lays with the flooring producers to be willing to have such a minor downgrade in the product while applying the secondary raw material, the secondary PVC. And then it comes to the market acceptance on the consumer side for flooring that contains secondary material or that is completely made of secondary material at eventually higher price. To find this out, we are currently carrying out a couple of surveys, so we are not finished with this yet. So the results you see here are preliminary right now and not yet published, so please bear with this, not take it for granted yet. But we identified that the consumers are not very much into the recyclability of flooring. So this is not a very popular theme for that waste stream or for that products. And also, if you think of the long lifetime of flooring, it's not something that easily comes into mind that your floor might end up with its lifetime and needs recycling. And also for the retailers, for the companies, it's not so much of a question if the recyclability of the product is really given. So we see that about like 30% do not see this as an important purchasing decision. And to sum up, there are, of course, some promoters needed. Happy to discuss this later as we perceived it until now. So definitely there are incentives for collection necessary that probably come along with enabling policies, maybe some sort of subsidies for the collection schemes or something like this. And of course, the floors themselves need to be designed for recycling so they can easily be separated. And as you know, material mixtures are not that easy to separate. And of course, to the end, it's all about the willingness to pay at consumer side. Is the consumer really willing to pay a bit more or considerably more? We do not know yet, for a flooring that is completely made of recycled material, or at least can be recycled easily afterwards. And that's it from my side. Thank you very much for your attention. And if you'd like to find out more, happy to meet you later, or go find us on LinkedIn or Twitter.
Melanie, thank you very much. Fascinating presentation. Once again, we see a huge area of, in inverted commas, waste and the potential for some really good reprocessing, recycling, and we'll see what comes of that project. It's exciting that there's so much going on in the building and construction world that is demanding that we are more thoughtful about our use and reuse of materials. So I think you're definitely swimming in the right direction with that program, and maybe there will be major players who can connect in on this sort of a project to really get things moving forwards. Talking of wastes in construction, our next project is a really interesting one, looking at another problem waste stream that generally ends up in landfill or and incineration, and that's glass fiber composite, or GFRP, which has been a growing problem. Waste from wind, boats, automotive and construction industries, and much head scratching about what to do with that. Well, Cecilia Mattsson, a scientist in the Division of Material and Production at the RISE Research Institute of Sweden. You are coming up, we hope, with some thoughts and some solutions in this. We like solutions in this world. So GFRP, composite waste, we have a possible way forward for this. Over to you, Cecilia.
Thank you. So, thank you for the introduction. Can you see my screen?
Yep, it's good.
Okay, so I will talk a little bit about how to create circular streams from glass fiber composite waste. And I will focus a little bit about chemical recycling and then reuse of these type of structures. So we are facing large challenges in this area. We have the wind turbine blades that's now buried in the US in the desert. And in Europe, we're expecting 36,000 blades within 5 years. But in Europe, you don't bury them as whole, you have to shred it first. And we also have a large challenge in the boat sectors that were built in 1970s, 1960s, and we also have a large stream of boats that need to be recycled. Approximately 30% needs to be recycled. And today, the problem is that the last owner are responsible. And we have no recycling solutions, and the waste is going for landfill or incineration. And both are contributing to landfill, because when you do incineration, you get ashes of the glass fiber. And the glass fiber is the major constituent in this type of products. So in Europe, at 2025, it's estimated to be 700,000 tons of composite waste. And it's only not the marine and the wind sector, it's also the building and construction, electrical and electronics and transportation sector that's facing this type of challenges. We need to find new recycling solutions for this type of waste. So here is an overview over existing recycling technologies. And at my project at RISE, we focused on the new technology, chemical recycling, and we specifically worked with subcritical water, so-called solvolysis or HTL. But we realized it's really hard to release the glass fiber from this dense structures. And we soon started to work instead with reuse options. We believe instead, why should we destroy this type of materials when they still are mechanical strong? So we think we can give this type of structures a second life, and we specifically think about the wind turbine blades. We can do playgrounds, bridges, and other type of constructions. So I will talk a little bit about the chemical recycling because this is my focus area. And on the picture here to the right, you can see a piece of a blade, A. And it not only contains glass fiber composite by thermosets, it also contains this piece, balsa wood. But you can also have thermoplastics, like the previous speaker. A large problem in this area is also the PVC, because the PVC is usually a foam core and this type of materials. But in this piece, it didn't exist, the PVC, but we could separate out the glass fiber, and the thermoset it's transformed to an oil product, and then we also can separate out the wood pulp. But the problem with this type of recycling is that you need long reaction times, it's 20 hours, and we work at high pressure and temperature, 270 degrees and 175 bars. And you need to have high value products out of this type of recycling systems. And the problem is that glass fiber, new glass fiber is cost €1 per kilo. And recycled glass fibers have not the same quality or size that cannot drive this process. And also then on the other side, we have the solubilizes oil that could be a substitute in the future for fossil oil into the fossil-based refineries. But the amount of oil that you can receive from the wind turbine blades is maximum 30%, because the blades are composed of 70% of glass fiber and fillers, and the plastic part is only 30%. So that means we have a large problem to develop these type of processes. Instead, we have been focused on why can we not give this type of structures a new life. So we have focused on the blades, and in Europe it's built a few demonstrators, mainly in Netherlands, and they have built playgrounds and also benches. And other groups also in the field have made some kind of roofing. And we also would like to try this concept in the projects in Sweden. So we have focused on bridges. We think that we can replace the existing materials in bridges with old wind turbine blades. So we, together with Sweco and Chalmers, had 4 master students in this theme. But we have not built the concept bridge yet. We only have applied for funding. But this thing is a future concept because the blades are mechanically strong and they can live after 25 years as a wind turbine blade, but probably can live 50 years as a bridge. We're also aiming to build a demonstrator, and we have found a possibility to use old blades that we found in Sweden. So we should use the tips for build a lane divider at a small recycling facility in south of Sweden, and where we should replace the concrete sows that we usually have as lane dividers, and use the tips and have a centerpiece of a stone. And this would be our first demonstrator in Sweden, and it probably will be built during the spring. So also concepts regarding manufacturing waste, and here we don't have the problems with the end-of-life waste. And this project, we focused on old or manufacturing waste from ABB insulators, and also from bathroom producers, P.h.D in the northern Sweden. They built composite bathrooms, and they take out a piece for the door. So by combining these two pieces, we can do new composite bridge deckings, like you see to the right. So we combine these two waste streams, and it's done by Marström and Composite Design in Sweden. And here you don't have the problem of the end-of-life material. It's like production waste. So the classification will be much more easy to drive this kind of streams. So to conclude, we need to develop new waste valorization systems for this type of waste from glass fiber composite structures. And we at RISE have focused on the technical solutions of recycling and reuse, but we also need to work over the whole value chain. We need to develop waste sorting systems, digital tracking, logistics. We also need to take a bigger picture about the system perspective and the legislations. And also to find new products that we can reuse, both the recycled products, not so good glass fibers and the oil product, and also the whole parts. So we need to be really innovative in the future to find value in this waste stream. So thank you for your attention, and here the project that financed this work. You're muted, Peter.
There we go. Strange things happen there. They do online. Really interesting. I love the concept of a wind turbine bridge. Sometimes we need something kind of creative, imaginative and visionary to kind of draw thoughts and ideas in. So good luck with that one. And again, if you're interested in that area, then Cecilia will be in one of the breakout rooms to have a further conversation. So we're going from having looked at some particular tricky waste areas and the possibility of circularity to talk about a network and the circular design network in Finland, which is looking particularly at those data gaps, which are one of the thorns in the flesh of trying to do more effective circular design. And we're joined by, and I'll try and pronounce this right, Päivi Kivikytö-Reponen, that'll do, hopefully,
yes,
from VTT Technical Research Centre of Finland. And you're very much trying to pull this network, circular design network together. So very interested to hear about the work that you're doing there in closing some information gaps.
Thank you, Peter. And I will share first my presentation. So hoping you are seeing this now.
Yep, that's good.
Yes, good. And I'm happy to be here and present this to you. So I will talk about the circular design network, which we are now building in Finland. So we have quite national perspective here. This project is funded by Academy of Finland, and we have 5 partners, so University of Aalto and 4 research institutes, GTK, Luke, Syke, and VTT, so Technical Research Centre of Finland. And if I first start a little presenting the idea of what we have here as a back what is behind our thinking here. Our network is focusing on design. So we are not so much talking about generally circular economy, but we are focusing on certain or circular economy design strategies, circular design strategies for slowing the loop, closing the loop, narrowing, and also retaining the value. And of course, we go then quite much deeper to the specific issue on ecosystem level, business level, and product level. That's like a big picture, what we have here. And as we are talking now about the really big subject and new subject, and also one of the first attempts to connect actors and stakeholders in Finland to around this subject. In this our project, we currently have when we applied this, we got over 30 companies and stakeholders to support us, and ongoing when we are now going on, we are reaching about 70 to 100 stakeholders to be here in the ecosystem, and actually on person level that means several hundreds persons to be involved, and also like to be familiar with this subject in companies and in other stakeholders. And also in university and research institutes, we currently have active project members of 80 or near 70 to 80 at this point, who are really working on this subject daily. Yes, as we heard here earlier about the several design strategies, how to design out waste and how to design with the secondary raw materials. Here I actually like to also I like to concretize this somehow, what kind of process that is in ecosystem, and in that level, in system level, how many streams and, for instance, secondary raw material streams there are needed, and what kind of material streams and actors are needed to support the business case, and how we create the value. And then there is this product scale eco-design. For instance, this what you saw here is kind of same process what we heard earlier or already presented by Marjaana Karhu, how to create value from the mineral side streams. So there is something about my mouse. Yes, now I got the next slide. As we have in this network, we strongly have our idea is to create value from data, and we utilize also like modeling, different kind of modeling tools to understand the systemic impacts. Here is some demonstration about the modeling and simulation, which we also actually heard today, what kind of probably different approaches are needed in dynamic systems compared to static or analytic smaller scale problems. So that was kind of intro to understand what or intro to think about our focus in circular design, and how we actually what we are doing. We are looking for needs and sources of data, how we support circularity through data, and the aim is also what we are now building. At this moment, we are building 3 demonstrations, so 3 minimum viable products to show then and concretize then both the experimental ways to design in circular design, and digital tools how to support circular design. And here is some structure of the what kind of actions there are in the project. So I will actually skip this. and start to show about the data for circularity type of approach what there is now going on. We have there a lot of stakeholders interviews going on. Then we are looking about the different kind of data sources. So data sources which are available publicly, but also data sources which are probably not so public, but there is some potential to still use that data. And then we have like called think tanks or workshops coming for certain topics. We actually concentrate for a little narrow topics like batteries, textile, plastics, and carbon cycle in food. So that we are looking for gaps and opportunities of the stakeholders in these value chains. Of course, we have a couple of years also. We have had like circular economic community activities around this, around the partners what we have now, and we utilize all the old roadmaps and we will build the system pictures of these value chains. Yes, that's like a summary. What is there going on currently, and it's possible, and we really want to also cooperate outside Finland with this, and you are happy to visit our website and contact me, and it's possible to come this community to change the ideas and look for opportunities. Thank you.
Päivi, thank you very much. Very interesting, and there's no doubt that the future is going to be very much about these types of networks, connection, more effective information gathering and sharing. So we wish you well in that project, and I'm sure there'll be people who will be interested to connect with that project, potentially making it a Nordic success story. So we shall see how things develop on that on that front. Okay, carrying on through our wonderful odyssey of different programs and projects. Really fascinating, the range of activity taking place. Obviously, as we move further towards circularity, product life cycle management becomes a more and more important thing to do, and actually modeling different interventions and different ways we can make change right through from design through to production, offer us possibilities of resource efficiency and moving towards circularity. And our next project looks at ICT in support of product life cycle management, modeling and activity. And delighted we're joined by Niloufar Salehi, who's a Ph.D. student in production engineering at KTH, Royal Institute of Technology. So Niloufar, great to have you with us, and very interesting to hear about the work you're doing in what is a very important and big topic area. So 8 minutes to give us a sample of some of the activity that you're involved with. Over to you.
Thank you very much, Peter, and good afternoon, everybody. I'm going to share my screen, and please let me know if you see it as it should be.
It's good.
So having heard about different type of physical flows, material flows so far, I'm going to emphasize on the importance of the information flow when we want to go circular in manufacturing systems and through the whole value chain of manufacturing a product. So as it was explained and discussed in the first presentation by my colleague Malvina Roci, so circular manufacturing system in the context of both manufacturing, production, and also circular economy, is a system that is designed intentionally to close the loop through multiple life cycles and preferably to maintain the material component and products in their original form. Circular manufacturing system consists of three main functions or pillars, that is product design, business model, and supply chain. That's to implement circular economy in the manufacturing systems. We need these three functions to interact with each other dynamically, and we need to avoid that each of these functions to work in solo. So each of these functions affect each other, both at the individual and aggregated level. So at the end, we can consider it as a complex system through the whole value chain of a product, and that we need an enabler to enable their interaction and communication through the whole value chain. So if we look at the value chain of a product from the beginning of the life cycle to the end of the life cycle, we can see that we can have the design and production in the stage of beginning of the life, and then maintenance, use phase, and distribution in the middle, and at the end of life we can have reuse, remanufacturing, and at the end it will be disposal. And as you can see in the picture, so all of these sections have interaction with each other, and they are interconnected with each other. So it is important that they could disseminate the data and the knowledge among each other, and it should be, this data and knowledge should be interpreted and analyzed and help each section to decide accordingly and to act proactively. So as I mentioned, multiple life cycle products is one of the main features of circular manufacturing system. So multiple life cycle products are the other ones that needs to be returned to the manufacturer, and it needs the recovery, the value recovery of these products need to be planned according to the design and to the business model of these products. So it needs a proactive approach. It needs the information flow to be disseminated through the whole value chain, through these cycles. I can give you an example from the RECIPS project that you can find a link in the virtual booth of CE at KTH in this conference. So the white good demonstrator in our project RECIPS, they are working on a product, on a washing machine product, that the business model of this product is paper wash, and it is designed for connectivity and for value recovery, that is refurbishing and remanufacturing. So, and they need to set the their circular network design in a way that they can get back the product with a certain quantity at a certain time and with a certain quality. So they need ICT devices, information and communication devices and tools to have the life cycle traceability, so they can provide a better predictive and preventive service to their customers, because paper wash is a service-based and service-oriented business model. They also can have information about the customer behavior, so they can incentivize or disincentivize their customers, so they can improve the environmental and also economic performance during the use phase. The OEMs, the white good demonstrator, also can get reliable information by using ICT platforms and the devices that they put in their product as they are designed for the connectivity, to get reliable information about the product value recovery, to decide if it needs only maintenance, refurbishment, or remanufacturing. So with the use of ICT through the whole value chain of a product, we can have an active lifecycle management of a product. It means that you can have information, real-time information during the use phase of the product, like the washing machine, and then you can give suggestion to your customers during the use phase. That was like previously, it was we have this information gap in this phase. So instead of having reaction after what happened. So you will be proactive and decide accordingly with these tools and with considering information flow in your decisions. Another aspect of information and communication tools are modeling and simulation that I'm majorly focusing on in my work as a decision support tool and as an analysis method for the manufacturing system. So physical and financial flow were always part of the modeling and simulation. But what I am focusing and emphasizing on is that information flow shouldn't be granted, and it should be considered in the modeling and simulation. So by considering the effect of transparency in the system, we can have a better idea of the environmental, economic, and technical performance of the system. Again, as an example, the other demonstrator in our project, RECIPS, was an automotive demonstrator that multi-method model by considering the information flow was developed to define and to model their new business approach, as it is streamlining their reverse logistics with the support of a cloud-based platform. So they could manage the inefficiencies by having the transparency of the information and information flow in their system. So by this modeling and simulation, we could tell them how much their economic performance, environmental and technical performance will be improved. In terms of, for example, in the technical performance, we could tell them how much leakage would be reduced and how much the lead time would be improved. Another strategies that help the circular economy is industrial symbiosis. That to develop industrial symbiosis, we need information flow. We need the stakeholders together and to establish a cooperative and collaborative environment. But for that, we need an IoT platform to disseminate this information among them, so they can, for example, the excess material of one of the companies could be the resource of the other one. But to know this information, they need to gather together and they need to collaborate with each other. And in this project, CIS Sutenes, we are working on developing an IoT-based platform to make this collaboration among these companies. Another tool that can be part of the ICT information and communication technologies are the material passports, that they can boost these interactions among stakeholders, because by using material passports, we can have the characteristics and identification of the material and components through the whole value chain. And in this tool, we can use AI, blockchain, different type of databases to register and to follow the value of the material component and products. And then by providing or kind of, I would say, material matchmaking between different companies and industries, so we can avoid unnecessary disposal and excess material of one company that I don't want to call it waste, could be a resource for other companies. So here as well, information and communication technologies can be a help. So I try to categorize the opportunities and challenges of information and communication technologies in these 3 stages of a life cycle. For example, if we use these type of technologies at the beginning of the life cycle, we can have innovative design, because based on the data that we gather, we can improve our design for value recovery. Or for example, in the middle of the life, we can maybe I need to make it a bit shorter, so we can discuss it. Sorry, my presentation doesn't work. Yeah, so maybe I can go to the conclusion. That's we see ICT as an enabler through the in the circular manufacturing systems by considering these three main pillars: business model, design, and supply chain, because it can enable a strong interaction among these three pillars, and it can ensure us about the information availability, reliability, and transparency by providing the infrastructure for acquiring the data, tracing and tracking and analysis and interpretation of the data and information that we can gather through the whole value chain. Yes, thank you.
Niloufar, thank you very much. Another fascinating project, so much to explore in that. And you'll be able to connect with Niloufar if you want, just after our final presentation. And for that, we are heading to the world of biorefineries, because pulp and paper generate huge amounts of process effluent. And this project is looking about whether we can utilize these effluent streams to a positive circular effect. So I'm hoping that Sudhanshu Pawar, who's a researcher and technology developer at RISE Research Institute of Sweden, is with us. Yes, you are. So mucky old effluent, huge amounts of water going into this system. Can we do something positive? You are our last presentation. So great to have you with us, and over to you.
Thank you. Thank you very much, Peter. And thank you for pronouncing my name correctly. And as you say, as a last speaker, then I have a freedom to take time.
No.
I'm joking, of course. So yes, I begin with sharing my presentation, as you can see here. Hopefully quickly now. Yes. As Peter kindly introduced me, my name is Sudhanshu Pawar. I work as a researcher at RISE. I'm working with currently 4 bioprocess technologies and developing them from, you can say, from drawing board to demo scale. And one of them is biohydrogen technologies, and which is part of this project. So the project is multi-bio, multi-purpose biorefinery in a pulp and paper industry. There we had several pulp and paper industries, Rottneros, Billerud-Korsnäs, Stora Enso with us. We also had fish meal company, God's Fisk. They also, of course, grow fish. And Fortum Resources and Waste, they are technology developers. Promico, similar as Fortum, technology developer. Drenor, also a small new started company. And then several universities such as Karlstad University, Swedish Agricultural University, and Lund University with us. And we ourselves RISE and Paper Province, a non-profit organization working with different pulp and paper industries. And the project was funded by Vinnova. So then I will first talk about aim and objective of this project, technical developments we managed to make in different areas, and feasibility studies, and eventually concluding remarks and future continuation of this project. So aim, simply Multibio wants to produce biological hydrogen, biopolymers, and sustainable feed ingredients for aquaculture or fish production, and eventually clean water in a cascade process. So today's theme is, of course, circular economy that several speakers talked about, and this cascade process is part of a circular economy where you can recycle water and recycle nutrients. At the same time, you can produce different products. And by doing so, this concept could fulfill several of the United Nations sustainability goals. So that was the aim. And the concept here, as you see, is to currently, most of the pulp and paper mills, the processed water, the effluent water directly goes to a treatment plant, the biological treatment plant, and then it's cleaned, well taken care of. Our hypothesis is that part of that wastewater, whatever is feasible, if it is diverted to our concept, then we could produce biological hydrogen in the first step. That's where hydrogen is produced as a gaseous product. Then you have effluent, liquid effluent that goes to the biopolymer process, as the effluent contains acetic acid or acids that are easily used by the biopolymer process. And the third part is the solid part, that's the microbes that produce biological hydrogen in the first step. Those microbes could be used as a component for production of fish feed. So this is basically the concept. And doing all this, the water that leaves the last step, that is the biopolymer process, is relatively cleaned, and that means the biological treatment of the existing facility will not need so much input of chemical and energy, and it will be simplified cleaning process. So that was the concept with the project. And I'll begin with biohydrogen process. To go quickly to main developments and conclusions we had was only one of the streams, that is fiber-rich CTMP effluent stream, that could be used in our process without any dilution needed. Microbes, the bacteria were compatible to that water, and so we got encouraging results in that, and we also managed to do experiments in a industrially relevant reactor, UA reactor, with a good productivity of hydrogen. Another aim with the lab project was to develop methods for scale up of the process, which was done later on. We also looked at feasible nutrients, for example, urea as a nutrient for microbes. That meant we could minimize the cost of the process very much. And then fiber sludge as a carrier for biofilm. So biofilms of these microbes were relevant because as you produce biofilms, you improve the productivity, space-time yield of the process. And in that, instead of plastic carriers, could you use fiber sludge? So that was also looked at, and indeed they could be, but we couldn't verify that through a microscopy process. But definitely we saw the difference in the process when we used fiber sludge as a carrier. Then, of course, that led the initial work in the lab led to the pilot scale process. We had to be careful about the safety aspect of the hydrogen gas, and we needed ATEX classified facilities. And then the aim was to also produce biomass, enough microbial biomass that could be used for fish feed trials. So we modified the existing facility of a company close to here in the ends, and there we managed to produce or scale up this process. So eventually, to conclude the development there, we saw that the Callicellulosiraptor species that typically we use for biohydrogen process are robust and adaptable, and it was easier to grow them at pilot scale, contrary to our assumptions. And methods we developed were very easy to scale up, and we increased the TRL level of the process to 4 to 5 almost, and we produced more than 2 kilos of biomass, and this was only with a 400 liter reactor. Initial plan in the experiment was to use 10 cubic liter reactor, and but that could not be used due to safety concerns. So there we also saw how economy of scale works. With the same cost, we could have performed experiments at much larger scale, but because of the safety concerns, we had to bring it down to 400 liter. Yes, so the concluding remarks for the biohydrogen process, CSTR reactor showed better performance, but UA is more relevant, and it could be better results could be obtained with further experiments. The maximum rate we saw was 13 millimolar of hydrogen produced per liter per hour, but our calculations suggest that it has to be 10 times better, at least. Pilot run, as I mentioned earlier, we managed to scale up the process and we obtained sufficient biomass for fish feed. So that was the biohydrogen process. Then going forward to biopolymer process. So as I mentioned earlier, the effluent of the biohydrogen process contains easily digestible acids, mainly acetic acid, and that is relevant for PHA process. That was already evaluated in project leading to this. So instead, our aim was to look at the which streams again could be applicable to biopolymer process directly. Before jumping into that, a little bit of introduction here is biopolymers.
You've got 1 minute, I'm afraid. We're right out of time. So
all right, I'll go forward quickly. So sorry. Basically here in the biopolymer process, we looked at experimental results as well as mass balance, and we found out that a good amount of more than 2,000 tons of biopolymer could be produced in through one of the streams. And we also looked at fish meal, and there basically CAULDRON cells were good. But more detailed experiments are needed. Same experience we had with PHA or biopolymer as a ingredient, and there also was similar results that we needed further experiments. Feasibility studies, now I have to, I think, jump into concluding remarks directly. Yes. So there,
very swiftly, 30 seconds if you can.
Absolutely. There basically only PHA process looks to be more applicable, more that implementable within next 5 years. The whole multi-bio concept, we need to make more further developments before it can be implemented. So that is the take-home message from here. Yeah, with that, I thank you all.
Brilliant.
And hope to talk more in the...
So there's some fascinating results emerging there and potential for scaling up. Sorry to rush you at the end, but I do want to give everybody a chance just to connect up. So let me tell you what's going to happen now. Basically, if our speakers would like to click on the link on the right and go then choose their own presentation and go into that room and host a conversation. Everybody else, if you can push the participation link on the program, that will hopefully get you into a choice of the speakers, and we've got just under 15 minutes for you to be able to have a one-to-one conversation. Whatever happens, I'm sure you'll connect on the website or email or whatever else, and we're going to be back here at 4:15 for a final slightly controversial discussion of circular economy. Thank you to all our speakers. Really brilliant, really fascinating. Make your way to the breakout rooms now, and hopefully you'll have 10 or 12 minutes of further conversation. So thank you all very much, and no doubt see you later. Thank you.